In this screencast, we are going to identify functional groups using molecules that are commonly seen in cosmetics products and talk a little bit about the molecule itself and where it's found. So before we begin, we're going to talk just kind of generally about functional groups. Functional groups are important because they help us figure out how a molecule reacts, right? So functional groups are just groups of atoms that help us determine how they react. Generally, functional groups can be recognized because, so generally functional groups can be recognized by, let's say by instead of because, by the fact that they contain heteroatoms. And when we talk about a heteroatom, that is an atom other than carbon or hydrogen. Or double or triple bonds. So, for example, if I look at vitamin C is a molecule that we talked about in another screencast, and I go through to identify the functional groups, I am going to look for things that are not just carbon and hydrogen. So, for example, there's this OH group here. This is a functional group called an alcohol. We're going to talk about that in another slide. So you can see that vitamin C has 4 alcohols. You can also see there's a double bond here. That's a functional group called an alkene. It is one we will talk about. And then you can also see that we have an oxygen next to a carbon double bonded oxygen. That's an ester functional group, which we are also going to talk about later. So molecules, so all of these functional groups can help us predict how this molecule is going to react. And molecules can contain more than one functional group. And many of the ones that are used in cosmetics do. Before we jump into kind of functional groups, I want to talk about an abbreviation that you'll see every so often. Every so often, you're going to see this R abbreviation. So, for example, if we have a carboxylic acid functional group, which is a C double bonded to an O with an OH, the reactivity is really here. So, when we look at, for example, acetic acid, which is the molecule found in vinegar, or palmitic acid, right, which is a fatty acid here, both of these contain the functional group, the carboxylic acid. So they're in the same family of organic molecules. And so we can abbreviate this molecule and this molecule just as R if all we're doing is talking about the functional group. So every so often you're going to see R, and we can kind of think about R is just a general abbreviation for the rest of the molecule. Right, and so that's what we're going to see there. So without further ado, we are going to jump into our functional groups. The first functional group that we're going to talk about are alkenes. Alkenes are a carbon double bonded to a carbon, okay? So this is a carbon-carbon double bond. We can recognize them in their names because generally the name will end in E-N-E. So instead of our alkanes, which end in A-N-E, these molecules are going to end with the name in E-N-E. And so, for example, we have beta carotene here. You can see that E-N-E ending, and you can see all of the double bonds which are shown here. That is a common molecule that is in carrots. We talked about that as a vitamin A precursor in a previous screencast, but you can see the double bond functional groups here. We also have things like alpha pinene. You'll notice it ends in the E and E ending. This is the structure of alpha pinene. It has a double bond. That's the pine fragrance that you'll smell a lot of times. And then we've got limonene here, and you can see the double bond there, and that ends in E and E, and that's responsible for a lemon fragrance. Often these are used in perfumes, right? And so that's where we'll see those be used. Let's talk about two other molecules really quickly that are used in cosmetics. One is squalane. Okay. This particular molecule is a larger molecule with multiple double bonds. It's actually classified as something called a triterpene because of the way the double bonds are arranged. It's a colorless oil. If you have an impure sample, it kind of picks up a yellowy color. It was originally obtained from shark liver oil. Which is why it's called squalene. Squalus is a genus of sharks. Okay. And so we also naturally produce squalene. About 12% of squalene, bodily squalene found in humans, is found in sebum, which is the oil that's on the skin, and we talked about that previously. So squalene here has this role in topical skin lubrication and protection. Now, while squalene contains these alkene groups, you'll often see squalane as an ingredient in cosmetics. Right. Now, this is the hydrogenated form of squalene. Now, we may have heard of hydrogenated oils before, particularly in your food products. Basically, the way this reaction works is you have the molecule with the double bonds, you bubble in hydrogen gas with a catalyst, right? And all the double bonds are replaced with single bonds, right? So all your double bonds go away. This is called an unsaturated hydrocarbon, right? Because it has these double or triple bonds, those are called unsaturated hydrocarbons because they don't have the max amount of hydrogens that they possibly could. When it goes through this reaction, now it is considered a saturated hydrocarbon, right? So a saturated hydrocarbon, just as a review, has all carbon and hydrogen single bonds. So we go from an unsaturated to a saturated. So if you look at your cosmetic labels, a lot of times you will see squalane as the ingredient that's used. Another unsaturated hydrocarbon is an alkyne. Alkynes are not used or seen quite as frequently in nature. So they're a C triple bond C. That's what an alkyne is. They generally, if you're looking at the name, it ends in YNE. My absolute favorite example that doesn't have anything to do with cosmetics, but I couldn't teach it and leave it out, is the poison dart frog. So the toxin on the surface of the poison dart frog contains these carbon-carbon triple bonds. So if you go to the Nashville Zoo and you go into the kind of herpetology area, the very first thing that you'll see a lot of times are these really colorful poison dart frogs. and they have these carbon-carbon triple bonds in their on their skin as part of a toxin. Now, but I really wanted an example of an alkyne that was used in cosmetics. And after some hunting, I found this guy here. When we look at this particular molecule, there is another functional group that's there, but the functional group that we're interested in is this carbon-carbon triple bond. This is kind of a weird structure because it's sort of like a half skeletal structure, half condensed structure. So I want to point out that at this kind of angle right here, there's a carbon. Okay, so that's where that carbon-carbon triple bond is coming in from. So then the name of this molecule is methyl 2-octanoate, and it's a ester, which we'll talk about later, but it's an allergen found in cosmetics. So several people, if you're allergic to kind of a strange cosmetic, it might be this molecule, because it's used for violet leaf floral notes. So again, the name here is methyl 2-octanoate. If an alkyne is combined with a different or an additional functional group, the YN shows up kind of in the middle here. And so that's what screams to us that this molecule would have a triple bond. And so that's what we would see there. Our next functional group that we'll see that's an unsaturated hydrocarbon are aromatics. Aromatics show up so much in cosmetics. You've probably already seen them in some of the molecules that I have talked about. Aromatics were named because originally they smell, right? And so when people discovered them, they were like, oh, well, these guys smell, we'll call them all aromatics. And later, as they discovered more, they figured out they didn't all smell, but the name stuck. Basically, as far as we're concerned, an aromatic is going to be a 6 carbon membered ring with alternating double and single bonds. So as far as we're concerned, it's a 6 carbon ring with alternating double and single bonds. It can be shown like this, it can be shown like this, but most often you're going to see it shown as a ring with a circle in the middle. And that's just a symbol for those alternating single and double bonds. Benzene is the most common one. It's the simplest one that we're going to see. It's a lot of times used as a solvent. And so you can see the structure here. It is a flat or linear structure. Another molecule that contains an aromatic compound as well as some other functional groups is called phenoxyethanol. And the functional group, of course, that we're interested in is right here. That's that aromatic functional group. And this is used in a wide range of cosmetic and personal products because it is an antimicrobial. Right? And so it's really effective against several different types of bacteria as well as the yeast, right? So it's also used a lot of times as an antifungal. So overall, it's used as a preservative to keep your cosmetics from spoiling. If you look at some of your this is a pretty common antimicrobial or antifungal. So if you look at your cosmetics bottles, you should see this on some of your bottles, particularly your shower gels and things like that. Next functional group that we're going to talk about are alcohols. Alcohols are a combination of O and H. Generally, they end, if a molecule has an alcohol, it can end in OL. That's one of the ways that we can recognize that. So one of the simplest ones, for example, is ethanol, which is CH3CH2OH, which is often used in cosmetics as a solvent. But one of the ones that is the most common is glycerol. Glycerol has 3 alcohol groups. So let me highlight those here, here, and here. Glycerol is used in a lot of things. It is used in toothpaste to improve smoothness, right? Skincare products, like shaving cream, soaps, and hair care products. And what it does is it serves as a lubricant. So it's that smoothing action and emollient. And remember, we talked about emollients when we talked about lotions. This is just a topical substance, right, that often will soften or smooth or moisturize the skin by forming a protective layer on the surface. So this forms a protective layer on skin, right? And was basically a moisturizer. Okay, so we talked about emollients previously. Glycerol is a really common one. It's also found in pharmaceuticals, where it's often used as a humectant. So in pharmaceuticals, which is also basically a moisturizer. It stops creams from drying out, right? And it's also found a lot of times in tablets and things of that nature. So we mentioned ethanol, which is often listed as alcohol, like denatured alcohol, are used in cosmetics as like solvents or preservatives. Ethanol particularly is associated with drying effects, right? So the problem using ethanol is it's got a drying effect, right? So it will dry out skin, especially in higher concentrations. And so that's why a lot of times you would use glycerol over the alcohols, right? And so that's why you would use one over the other. Other places that we see the alcohol groups are on fatty alcohols. And so these are 2 examples of what are called fatty alcohols. The reason they're called fatty alcohols is because the fatty part is the long carbon chain here, okay, which you see a lot of times in fats. We're going to talk about fats in one of our following screencasts. Despite having alcohol in their name, this long chain really gives them these waxy emollient properties. So they function as things like thickeners or emulsifiers or emollients rather than drying agents, right? So these are thickeners and emollients. So they are not drying because they have that long carbon hydrogen tail. So they're more like fats. But they still have that alcohol functional group, which we see right here and right here. The next functional group that we're going to talk about are ethers. These are molecules that have an oxygen in between 2 carbon molecules. So I'm going to use the R groups there just to show us carbon molecules. This is the simplest example of an ether. The name of this is dimethyl ether. Okay, it's got the 2 methyl groups on either side. You can recognize ethers because if they are particularly small ethers, the name will contain the word ether. If there are a lot of other functional groups around, you can identify a molecule with an ether as it's got a prefix, which is an alkoxy, right? So if it's got like this alkoxy prefix, that's where you're gonna see that. So dimethyl ether is the simplest ether. One of the ethers that's commonly used in cosmetics is this molecule right here. This is called ppg20 methyl glucose ether. Okay, so this is a molecule that's used as an emollient, a fragrance, fixative, right, and a humectant for hair and skin products. So that humectant part, it's going to hold and attract water, and so it's going to be very moisturizing for the skin and hair. So it holds and attracts water. And then the emollient part here is going to soften and smooth skin and hair. Right? So that means that a lot of times it's used in conditioning, like skin and hair conditioning. It just improves the overall feel and appearance of the skin. It's pretty mild, so it's suitable for sensitive skin formulations, and it's light and non-greasy. You will generally see this particular product in moisturizers and lotions, creams, and shampoos and conditioners. Right? You can see it highlighted here. You can see the oxygens are in red. So it has lots and lots of these ether. It's an alcohol group. Lots and lots of these ether groups that are shown here. It also has some alcohol groups. It is a polymer, which means there's lots of repeating units in it. It's also got a sugar unit in it here, and we'll talk about sugars in a podcast later, or screencast later. Let's talk about the next functional group, which are aldehydes. We can recognize aldehydes because they have a carbon, double bonded oxygen with a hydrogen. So by default, they either start at the beginning or end of a molecule because they've got to have that hydrogen there, and carbon can only form 4 bonds. They end in AL. That's one of the ways that you can recognize them. They've got 2 main purposes in cosmetics. Fragrance and preservation. All right, so they're 2 big cosmetics. Let's look at some of the fragrance ones. For example, we've got citral that's shown up here. The aldehyde part of that molecule is right here. We also have some double bonds. So we've got that alkene functional group as well. This is found naturally in the oils of like lemon. So it's a lemon fragrance. So it's found in lemon, lemongrass, and orange. It provides this kind of strong, fresh, lemony, citrusy scent. And so you find it in a lot of citral and floral fragrances. So it's common in like perfumes, colognes, lotions, shampoos, soaps, body wash, right? Any other fragrance product you can get, right? And so that's an aldehyde. Another common aldehyde that you'll find that's used in cosmetics is benzaldehyde. It's shown here. It is got an aromatic group. So I want to point out, right, that there's an aromatic functional group as well. Right? But we've got the aldehyde group. This is commonly used for if you need a cherry-like fragrance. Or almond. So it also gives off kind of this almondy cherry fragrance. So that's used pretty frequently as well in perfumes and things of that nature. Let's talk about preservation for just a second. Formaldehyde is a common, it's the simplest aldehyde. It only has one carbon. And it is used for preservation. So we've got formaldehyde, right? And it's got lots of antimicrobial properties. You might be familiar with it. It used to preserve specimens. So there's a brain that's preserved in formaldehyde here. But we're really trying to get away from using formaldehyde because it is a human carcinogen. So when we talk about something being a carcinogen, that means it causes cancer. So we want to avoid that. Now, what has happened though, or what's commonly found in cosmetics are things called formaldehyde releasing preservatives. These molecules slowly degrade over time to release small amounts of formaldehyde. And common ones that you can find on your labels are these molecules here. These are common examples of formaldehyde releasing preservatives that just slowly release formaldehyde over time, right? So the idea is to keep the concentration low enough to be effective against microbes, but ideally below levels that would cause severe harm. But there's a super huge debate in the cosmetics community about these formaldehyde releasing preservatives. And so that's something that you just want to be aware of. So what are these formaldehyde releasing preservatives? These are ones that will slowly degrade over time to release small amounts of formaldehyde, which will then act as that antimicrobial. This has popped up recently in hair salons, right? So there was Brazilian blowouts for a while, had some products that when heated, they were releasing lots of formaldehyde. And so that's places that you'll see this. So if you see these on a label, that's the reason they're there. Let's talk about ketones next. Ketones are a carbon double bonded oxygen, but instead of having a hydrogen, they're going to be in between two carbons. Generally, they end in ONE. So the name itself is going to end in ONE. They are generally used in cosmetics for their fragrance properties. They are less commonly used as solvents, right? The simplest ketone that we have is acetone. That's its common name. It's also called 2-propanone. So when we're talking about these endings, right, you're going to see the O and E here and here. That is what tells us it has that ketone functional group right there. So it's a ketone that's there. Acetone is most often found as a solvent, and it's used as nail polish remover. Okay, so if you're using acetone, it's going to help remove nail polish. Other kind of ketones that will pop up in cosmetics are camphor. This is called a bicyclic monoterpene ketone. So bicyclic just means that we have two rings. We've got kind of this flat ring here with 1, 2, 3, 4, 5, 6 carbons. And then we have this triangular ring that comes up here like this. And so that's the two rings that you see. But the reason that we're highlighting this molecule is because the functional group right here is that ketone, that C double bond O in between two carbon groups. Now, it has a pretty distinctive, kind of pungent, aromatic odor. It's found in the wood of a camphor laurel tree. A lot of times it's kind of that fragrance that's in mothballs. But it's used in cosmetics as a cooling, right, soothing agent, okay? So it provides like a cooling sensation when it's applied to the skin. So it's often used in muscle rubs, right? Or balms. It'll be in some lip products. That's where you'll find camphor, right? And it provides this kind of tingling or soothing effect. It's also what we call an anti-pruritic. And what that does is it helps relieve itching. So it's got like this tingling effect. All right. So again, it's common in lip balms, vapor rubs, some foot creams. This is where we tend to find that. Our next functional group are carboxylic acids. We have run into carboxylic acids a little bit when we talked about weak acids in the previous chapter. So these are weak acids. We recognize these because they have an R group with a C double bond O, OH. But we remember that this is kind of a tricky functional group to recognize because it can also be shown as this or it can be shown as this. And so you don't want to let that throw you off. If you're just looking at the names, like if you're looking at the labels, generally these are shown where they end in OIC acid. So they will have some sort of acid there. So for example, this is glycolic acid. That is the common name, and you can see I found a glycolic acid serum. The formal name for this is hydroxyethanoic acid. So we have kind of these common names and then more formal names. When we're looking at the carboxylic acid group, this is the carboxylic acid group right here. Now, it's also got an alcohol on it. That's where, for what clues us in that it's got an alcohol is this part of the name, that hydroxy lets us know that, hey, we've got an alcohol there. The oic acid here lets us know, hey, look, that's a carboxylic acid. And so that's how we know that there are two particular forms. Now, glycolic acid is something called an alpha hydroxy acid. So alpha hydroxy acids are just a really well-known group of carboxylic acids that also contain a hydroxyl group. So these contain the carboxylic acid with a hydroxyl group, which is that alcohol functional group, okay? And that alcohol functional group, the reason they're called alpha is because that's located on the alpha carbon. So the hydroxyl group is on the alpha carbon. The alpha carbon is the carbon next to the carboxylic acid. So we've got this really specific location. So when we look at this carbon right here next to the carboxylic acid is the alpha, and that is where you have the OH. So if we look at this molecule down here, this lower one, which is lactic acid, we find our carboxylic acid group here, and then we recognize this is an alpha hydroxy acid because on the alpha carbon here, there's an OH. So that's how we know these are alpha hydroxy acids. They're a lot of times abbreviated as AAH, particularly when you see these in skincare. So without further kind of ado, let's talk about what they're used for. They are generally used for exfoliating, and because of that, some anti-aging creams, right? So when we look at glycolic acid, which is here, we see this glycolic acid serum or cream, and basically it's got glycolic acid in it because it exfoliates the skin by loosening the bond between dead skin cells. So this exfoliates the skin by loosening the bonds between dead skin cells. And this helps promote cell turnover, and that leads to like a smooth texture and brighter skin and the reduced appearance of fine lines and wrinkles. It also improves hyperpigmentation. So glycolic acid, when we look at that particular molecule, we get a smoother texture of skin. Right? Brighter skin. Reduced appearance of wrinkles. Right? And it improves hyperpigmentation, which are age spots. Okay, so it's kind of these weird dark spots. It's commonly used in things like chemical peels, serums, toners, cleansers, moisturizers, especially those that are targeting anti-aging or reducing dullness in your skin. So you're going to see AHAs show up pretty frequently. Lactic acid, which is the one right down here, is another one that we commonly see. It's found naturally in sour milk and fermented foods. It's larger than glycolic acid, so it's used because it's a bit milder than glycolic acid. And it's also a humectant. It mostly exfoliates and brightens. So if you use a gentle exfoliator, then lactic acid is probably in there. It's also used in moisturizers and things like that. So when you see AHAs or alpha hydroxy acids in cosmetics, they are working to break down or loosen the bonds between those dead skin cells, and it helps your skin cells turn over. And so that's why we see those. And they contain a carboxylic acid. Let's talk about esters. When we talk about an ester functional group, we are going to see that it has an R group with a C double bond O, an oxygen, and another R group. Now, I want to remind you the order doesn't matter. So sometimes they can show up and look like this, right? So just kind of watch for that. I've got two molecules here. This is that ester functional group. This is also the ester functional group. We recognize these because a lot of times they will have an ATE ending in the name. So for example, we've got benzyl acetate. This is the benzene ring. That's where we get the benzyl from. And then the ATE ending is because we have this particular arrangement of atoms. This is ethyl butyrate. We've got that ATE ending again. We see that here. Esters a lot of times have this kind of characteristic fruity, floral, or sweet aroma. And so they are used quite frequently for fragrances. Benzyl acetate is just an ester of benzyl alcohol and acetic acid. And I have this image, and this is from a perfume company that sells esters. And the reason we see a flower on there is because this particular fragrance is a lot of times described as sweet, floral, and it says it's kind of like a jasmine-like or apple fragrance, right? And so that's the scent that it is marketed as. So these are really common in things that are scented: perfumes, soaps, detergents, any sort of fragrance products. Another one that's really common is ethyl butyrate. This has a fruity odor, right? And it's reminiscent. A lot of times people say it's like pineapple. I've had students who have tried to synthesize this in class, and we get varying degrees of success. About half the people are like, "Oh, it smells like pineapple," and about half the people say, "Oh, it smells like burnt grass." So we're sometimes successful. I grabbed this image from the company that was selling this, just to kind of show you how it's marketed, because I think that's kind of interesting there. Our next group of functional groups are amines. These are pretty nice to recognize. They have a nitrogen functional group in them. The thing that's kind of tricky is that the number of hydrogens. So they can either have 3 R groups, so 3 carbon containing molecules, or a nitrogen with 1 hydrogen and 2 R groups, or a nitrogen that has 2 hydrogens and an R group. Now, if it's a nitrogen with 3 hydrogens like that, that's just an ammonia molecule. Not to be confused with NH4+, which is our ammonium ion. So there's a couple places we can see nitrogen pop up, right? But most of the time, these in cosmetics are used as pH adjusters. These are weak bases. So they're used to increase the pH of different substances. So it neutralizes those acidic agreements to bring it to kind of a more products to a more skin-friendly pH range. These are also a lot of times used as emulsifiers, right? To help mix the oil and water components, right? That are commonly, we see emulsifiers used commonly in like creams and lotions, and sometimes they're used as surfactants. So these are common in things like lotions, creams, cleansers, shampoos, mascaras, sunscreens, and lots of other emulsion-based products. The one that's pretty common is triethanolamine. The tri comes from the fact that we've got 3 of these ethanol groups here surrounding the amine, which is that nitrogen. So that nitrogen functional group is shown right here. This a lot of times is abbreviated as TEA. So if you see the TEA abbreviation, that stands for triethanolamine. One of the things that's particularly problematic about this is this can cause a contact allergy known as dermatitis. So a lot of people are kind of trying to get away from this. It's particularly common. It's common enough that we at least avoid using it in labs and things like that. Another one that we see pretty commonly is the aminomethylpropanol. It's referred to as AMP. It's an amino alcohol. It's got the amine group shown right here with an alcohol group. It's a lot of times also used as a pH adjuster. It neutralizes. It can do all the same things. It can stabilize emulsions and really improve the efficiency of film-forming polymers. So that means then that a lot of times it's in hairstyling products, right? Because polymers are going to help with some of that hairstyling, but you can also find it in creams and lotions as well. Our next functional group are amides. We find amides in a couple places. Amides have a C double bond O right here, and it's directly attached to a nitrogen. So the nitrogen is directly attached to the C double bond O. We see it here and we see it here. And so there's some examples of where you would see an amide. when we talk about these, we see amides in a couple places. One of the places we see it is in this top molecule. You'll notice this top molecule has a negative and positive charge. It is a surfactant, right? It's derived from coconut oil and dimethylaminopropolamine. So it has a kind of amine-like structure, but it's technically called a Zwitter ion because it's got a positive and a negative charge. So it's a Zwitter ion. And so those charges cancel out. So it's got charged parts, but they cancel out. It's a really popular co-surfactant. It's known for its mildness. It's got foam boosting properties. So it helps some of those soaps become more foamy, right? So it's got foam boosting properties. And it a lot of times will reduce the irritation of other stronger surfactants. So a lot of times it's used as a milder surfactant. It is common in shampoos, body washes, facial cleansers, bubble baths, baby products, especially those marketed as mild or tear-free. So if you have some mild or tear-free, or you're walking through the grocery store and you look at the ingredients, this is a common ingredient that you'll run into. The molecule down here, the stearamidopropyl dimethylamine, is another group. It's the amido part here that lets us know it has an amide in it. Same thing here. So there's a couple ways to identify the names of amides. They can have an amido in the name, or it ends, the name itself can end in an amide, right? With just the word amide. These are often used as hair, this particular molecule is often used in hair conditioning products as an emulsifier, right? And basically, it will bind to the surface of damaged hair, and it'll provide like a smoothing or detangling or anti-static effects, and it improves the compatibility. So you find this a lot of times in hair conditioners or hair masks or some leave-in treatments. And so that's where we're going to find these amides. The last but not least functional group are our thiols. Our thiols generally contain a sulfur and a hydrogen. Their name will either have thiol towards the end or thio mixed in. Now, compared to all of the other functional groups, this one is not, you don't find molecules with thiols in cosmetics quite as much, because if you have a thiol group, it's generally they really have unpleasant odors. Think things like skunks, right? However, when thiols are used, they're generally for specific things to do using hair chemistry. So a lot of times they are used to break bonds in oxidation reduction reagents or processes using perms. So these are often used in perms. So let's talk about perms for a second. When we have hair, we have linkages between these sulfurs. So you see those sulfurs here. If you have a linkage that looks like this, that's called a disulfide. Okay, di just means two. These are linked. You can use a chemical, right, with this thiol group here, and it's called thioglycolate, and that will reduce the disulfide bonds in hair. Okay, So if you've ever had a perm, a lot of times what they'll do is they'll put a substance on your hair that smells really bad at the beginning, right? And when they do that, it breaks all the bonds. So all of these bonds are broken. And either they straighten your hair or they put your hair in curlers, and then it undergoes oxidation. So we've got an oxidation reduction reaction here, generally using hydrogen peroxide to reform the bonds in the kind of way that you want, right? And eventually these bonds will break and you'll be back over here, which is why you have to do these so often. So one of the ones, the molecules, we see the molecule here where it is a salt. That just means there's a negative charge with a positive charge. I have the molecule here as well. This is thioglycolic acid, right? The thio part is what tells us there's that sulfur group on it. The salt of this is what's commonly used to break those disulfide bonds in the keratin structure of hair. Now, another place that we see this, so we see it in perms, but the other place that we see this is in hair removal creams. So here, this will break down the structure of the hair in higher concentrations. And so when it does that, then it can easily be wiped away. So you find this in products like Nair. So those are that's really the only thiol that we see, and it's got two applications. One is hair removal, but one is also perms. Because it can also be used in hair removal, if you hear people talking about perms and losing a lot of hair during perms, that's the same reason, because it's the same molecule that's used in both. So this kind of ends our foray into functional groups. My hope is that you'll be able to look at a cosmetic label and read it and pick out what functional groups are in there from the name. My hope is that if you see a chemical structure, you'll also be able to pick out those functional groups as well. We'll talk more about this in class. If you have any questions, as always, please feel free to stop by my office.